Great. Hi, I'm Barbara Brawn. I'm the Associate Director for the Maryland Blended Reality Center. I'm going to give a lightning overview before I turn it over for my colleagues for a more in-depth look at a few of our key projects. Working with Amitabh Varshney as his research branched into blended reality, we kept meeting folks from various fields like arts and education, sociology and medicine, and everyone asked, have you tried VR or AR for this? And our answer was usually no, but let's. And it was in that spirit with our colleague Sarah Murthy at the School of Medicine and the Shock Trauma Center in Baltimore that we created the MBRC in 2017. This was made possible by generous funding from the Empowering the State strategic collaboration as part of their goal to foster and enrich collaborations between research schools at College Park and the professional schools at Baltimore. With the Shock Trauma Center, we've developed AR tools for critical care diagnostics, including our first prototype, AR for ultrasound, and subsequently AR-enabled catheterization for extraventricular drainage, patent pending, and AR for intubation, which we have field test results for and are publishing user study results. In collaboration with Ilana Koloka at the School of Nursing, we've explored VR for non-opioid pain management, including via immersive music modules created with the School of Music. Some of this work was featured in the January 2020 issue of National Geographic. With the Department of Sociology, we've developed VR training modules to combat implicit bias, creating over 80 different scenarios with the capability to capture user feedback and biometrics. Beyond empowering the state, our work has been generously supported by the Department of Defense, the Edward St. John Foundation, FDA, GlaxoSmithKline, NIH, NIST, NSF, and NOAA. And beyond National Geographic, our work's been featured in several news outlets, including NBC News, Voice of America, and Harvard Business Review. You can find out lots more about us and our work at mbrc.umd.edu. So thank you. I will take a breath and introduce my colleague, Sida Lee. Sida, it's all yours.
Thanks, Barbara. Let me share my screen real quick. All right, can you all see this? Okay, looks good. Hi, my name is Sida Lee, and I'm a researcher here at Maryland Blended Reality Center, and I will be introducing two of our projects today. So first off, we have the 360-degree 3D immersive performance. So this is the project that we've collaborated with Professor Irina Murisano from the School of Music to promote the democratization of the performing arts. And in this project, we have built a prototype immersive experience that represents her 4 Strings Around the World project. We wanted to use this project to demonstrate a new way of providing scalable and immersive experience. So here you can see this is a full 360-degree 3D VR experience with spatial audio. We created the immersive experience by fusing Irina's violin performance with multiple 360 backgrounds that we have captured. So although it might seem that Irina is performing outdoors, but in reality, we actually recorded her performance in a studio in front of a green screen. And this is under a very optimal acoustic setting for her violin performance. So different from conventional 2D green screen compositing techniques, in this project, we had to calibrate and account for depth in order to place her at the correct location in the 3D environment, so she doesn't appear as floating in midair. You might notice there are subtle changes in the lighting of her dress, as well as the direction of her shadow as we switch from one scene to the other. So everything we have done here is to most truthfully recreate the performance, allowing the audience to feel physically present right in front of our performer. The true immersive experience is best experienced in VR, where you can watch the performance in stereoscopic 3D. And another important aspect of this project is the spatial audio. The spatial audio we've recorded allows the audience to look around in VR and hear the audio change around them. This is not only limited to the direction of the audio source being stationary and consistent with the real world, but we're also able to simulate spatial audio effects such as echoing in the cathedral. Next up, we have this ultrasound visualization app that we have developed. So point of care ultrasound, or just ultrasound, is a rapid and low risk imaging option to provide quick diagnostic for patients. However, there's a lack of easy to use interface for collection of multi-zone ultrasound videos. We have developed this prototype in collaboration with Dr. Murthy to store, analyze, and display ultrasound images quickly and accurately. And we also developed this app, designed it in a way to facilitate clinical decision-making. We also wanted to use this app to build and maintain detailed ultrasound database of patients. And using these database and also the domain-specific knowledge of our medical partners, we're training machine learning networks to identify and quantify ultrasound findings of clinical importance. So the app consists of two different user modes. This is the input mode, where the physicians document one of the 12 zones one at a time as they perform an ultrasound imaging. And they can use this interface to leave comments and notes on their findings. And all of these findings, the comments, all the entries are stored in real time and linked with the ultrasound data for review in the future. And this is our review mode. So in the review mode, we've designed this intuitive body zone model to help navigate and display recorded ultrasound imaging. And doctors will be able to compare ultrasound image across multiple dates, or they can compare the different modalities, the high versus low frequency that's coming from the same imaging session. Comments and findings from the ultrasound examination session can also be reviewed in this mode, and doctors can put in additional edits and comments. And this really enables remote diagnostics and also collaborative review sessions. So finally, all of these ultrasound data are being trained in our AR software that automatically detects and identifies abnormalities. Here's a quick example of our prediction of abnormalities versus the ground truth. And this is just something that we're working towards. So up next, I think I'm gonna hand it over to my colleague, Eric Lee, to showcase some more of our projects. Eric?
Hello?
Yep.
Okay, sorry, I was muted. Okay, hi everybody, my name's Eric Lee. I'm another researcher here at the MBRC. Today I'm going to talk about two projects. The first one is a collaboration we're doing with CSIS. That's the Cooperative Institute for Satellite Earth System Studies. And what we're doing is exploring how virtual reality can be used for weather forecasting, specifically with 3D data. And throughout the slideshow, these are screenshots and recordings from our app. So our first goal is to allow National Weather Service forecasters to visualize weather data in virtual reality. We also want to demonstrate the value of 3D satellite data and VR in the forecasting and warning process. We want to identify best practices for meteorological visualizations in VR. And finally, we want to advise on vertical resolution requirements for future 3D data satellites. So just to show you what's currently being used, here's what National Weather Service forecasters currently use for forecasting. It's called AWIPS. And you can kind of already see the problem here. There's about 20 different sub-windows in this picture, all displaying different weather data products. Some of the windows you can barely see. So there's really limited screen real estate, and there's no capability to display 3D data. So all 3D data is projected down into 2D and displayed on these windows. And there's just a high mental load on forecasters to try and interpret this kind of data. So here's a screen recording from our software. So the first advantage that VR brings is the ability to analyze the 3D data in its native dimensionality. And from this intuitively reason about spatial relationships between different data. Also, using VR controllers, forecasters can manipulate and interact with data naturally by using body movements and hand gestures. There's an expansive visualization real estate afforded since we're not really confined to a 2D monitor anymore in a VR headset. Information recall has been shown to be improved in VR compared to a 2D display. And we just basically want to reduce the overall cognitive load on scientists and forecasters. So that's a really quick rundown of our VR weather project. The next project I'm going to talk about is creating highly realistic training environments in VR out of 360-degree images and videos. So here we have a few 360 images from the mechanical room in the Arib Center. And we've used these to create a demonstration VR training scenario with our technology. So what we do is we take the 360 images and we estimate different properties about the environment from them. So things like position and orientation of the 360 images, the distance between objects in the environment, the overall geometry, depth, scale, and lighting conditions in the environment. And instead of trying to do a full 3D reconstruction, we can augment the original images with virtual objects and the ability to navigate. So we can maintain that high level of fidelity and realism from the original images. So this is another video of the VR training scenario. And you can see the user can navigate between the different locations in the environment and maintain their correct orientation and relative positioning in the environment. We also insert virtual objects that stay fixed relative to objects in the real world. So they appear to live in the real environment. And the objects are also relit using estimated lighting from the 360 images, and they're able to cast shadows onto real world objects. So you can see the table here is casting a shadow onto the floor in the 360 image. So using this technology, we can create these realistic training scenarios that can be used to train people the same way that they would be trained in real life. So users can develop the same kind of spatial memory of the training setting that they would if they're training in the real world. People can be trained on processes that would be unique to a specific training setting. And the training can be scaled. So the scenario can be created once and used to train as many people as needed without scheduling or space constraints or the need to like shut down the real environment for training session. So that's just a quick, really brief summary of our VR training research. I'm going to hand it over to Jon, and he's going to talk about a few more things. Thanks.
Hello, everyone. So thanks, Eric. My name is Jonathan Heagerty, and I will continue with an overview of two more of our projects we are working on in the MBRC lab. So this first one I will discuss is the anatomy educational modules, which is a collaboration between the MBRC lab and the University of Maryland Medical Center at Shock Trauma. Like you have already heard from my colleagues, taking advantage and leveraging the virtual space can be tremendously beneficial. That is why in this collaboration, we wanted to try and take learning to the next level and create the classroom of the future. We wanted to create a truly immersive mixed reality education module for gross anatomy students as they go through their training. Today, when students or residents go through their gross anatomy classes, it can be crowded, creating a disadvantage for some of the students not being able to see a certain viewpoint or perspective. Also, when there is a unique case, pertaining to the dissection during their classes, if a student is absent, they won't be able to review it as if they were there. So moving on, we wanted to create these modules as immersive as possible and at extreme detail. We first started capturing dissections of cadavers with our colleagues Sarah Murthy and Adam Pouchet using traditional VR cameras, and we immediately recognized that these cameras had some limitations with regards to our work. So we decided to go with a custom in-house solution that would overcome the issues we encountered. What we created was a custom camera array that captures multiple videos simultaneously. These cameras are spaced independently from one another and at various IPDs. By creating the camera array in this way, we can capture stereoscopic video at closer proximity to objects within the scene and in return increases the detail on the cadaver. The other key thing here is including multiple cameras spaced at several IPDs. Generally, VR camera makers set a predetermined average IPD for their viewers. So with that said, if the user falls outside of this average IPD range, the individual could potentially experience discomfort and nausea in the VR environment. So with our camera array, we can cater to a larger audience. Lastly, our system captures at a 4K resolution, 30 frames per second. Having independent cameras and capturing at such high quality has proved a success for us. So I wanted to just touch on this briefly so you can have a visual illustration on how this educational module looks and the process to a final product. As you can see in the raw image, we have placed a green screen in the environment which will allow us to overlay text, images, and even 3D models to further aid in the immersive experience. As you can see on the right, we see a final version that is clear, close, and crisp. Moving on to the next project that I will cover is our cinematic video holograms project. What we wanted to do here is create a high quality static and dynamic 3D models of real life individuals and objects. Our goal here is to use our MULTIVIEW volumetric reconstructed models to revolutionize areas of industry to leverage the virtual space. As we have heard throughout the day, VR has significant advantages that we look to target with these vivid holograms. Some of the areas of industry we look to target are simulation and training, entertainment and sports, education, and virtual medicine. This research really ties in well with the work Eric mentioned previously with regards to the photorealistic virtual training modules. So now that we have covered a little about the why, I really want to dive into some of the behind the scenes for this project. Back in 2017, we started on the construction of our first volumetric capture studio. We created this studio using 64 cameras, capturing video at a resolution of 1640 by 1232. All 64 cameras were frame synced and captured at 30 FPS. Our reconstruction space was roughly 4x4 by 8 volume. As you can see in the video on the right, our virtual holograms are pushing the limits of photorealism. As I stated previously, these holograms can be used throughout industry as we can place these 3D models in any virtual environment. The last thing I would like to share with you today is our current status. We are pushing our project to the next level and capitalizing on what we have learned to produce our V2 volumetric capture studio, what we call the holo camera. We have increased not only the number of cameras from 64 to 300, we have also dramatically increased the resolution per camera to over 4,000 by 3,000 pixels. We have also increased the reconstruction space within the studio to a 7 by 7 by 8 volume. The goal in the studio remains aligned with our initial goal, but by having a higher density of cameras, we look to further emphasize the quality, precision, and detail of our models. We plan to have this operational in the coming weeks and are extremely excited to start working with this facility. I speak for the entire team when I say thank you for your time, and if you have any questions,